Hi guys, welcome to this screencast on linear motion. As you can see in front of you, angular motion, fluid mechanics, projectile motion is everything we have left to cover for A-level biomechanics. So this is the specification for linear motion. This is what we're going to be getting notes on during this screencast. So first of all, what is linear motion? So linear motion is movement of a body in a straight or curved line when all parts move the same distance in the same direction over the same time. For example, a 100-meter sprinter, or the javelin when the javelin has been thrown by the athlete in question. Now, we have to be aware of what linear motion actually results from. Okay, so linear motion results from a direct force being applied to a body through the center of mass. Okay, so that is what linear motion, or that is the result from a direct force that's being applied by the body or to a body through the center of mass. Okay, so we need to be aware of descriptions of linear motion. Okay, so we need to be aware of distance, displacement, speed, velocity, acceleration, and deceleration. So first of all, we're going to go through distance and what it is measured in. Okay, so distance is the total length of the path that the body travels from its starting position to its end position. It is measured in meters. So total length of the path covered from start to finish, ultimately. We then have displacement. So displacement is the shortest straight line route from start to finish. So the shortest straight line route in a specific direction from start to finish, and it is measured in meters also. Here is an example of the London Marathon. It starts here and you would run along this path like so. That is the distance covered, which is 26.2 miles. However, the shortest straight line route in the specific direction from start to finish, i.e. the displacement, is only 6.2 miles. Therefore, you can see displacement is different to distance. If we move on right now, we need to be aware of the definition, calculation, and units of measurement for speed, velocity, and deceleration. So speed, first of all, is the rate of change of distance, similar to acceleration. In terms of the rate of change in velocity, however, we have distance. The equation is speed in meters per second equals distance divided by time taken. We have got velocity. Velocity is the rate of change of displacement. Okay, and the equation for it is displacement divided by time, and it is measured in meters per second. Acceleration we know, okay, we've already done this, so I'll skip it off. However, deceleration we need to be aware of. So deceleration is or occurs when there is a decrease in velocity over time. It is the same equation as acceleration. I've got some examples here. You can pause this and go through them if you want to, so you can understand it. However, I will not be doing this right now during this screencast. So pause this now if you want to have a look at those and figure them out and work them out and make sense of them. It's pretty straightforward. Okay, we also need to be aware of graphs in linear motion. Okay, so we've got different types of graphs we need to be aware of. We have got distance time graphs, speed time graphs, and velocity time graphs. Just be aware that time is always on the horizontal axis, and these graphs essentially represent the motion of a body which is moving in a straight line or a curved path. Okay, so we have to be aware that these are visual representations of distance travelled, speed travelled, and velocity. Okay, so if we start with distance time graphs, so this shows the distance of a body travels over a period of time. The gradient of the curve indicates the speed of a body at a particular instance. So first of all, if the body is stationary waiting at a sprint start, we've got time on the horizontal axis and we have distance on the vertical. All that will be taking place here is no movement because distance doesn't change over that period of time. So this could be a period of 10 seconds waiting to start the race. So that is the gradient of the curve. It is in a straight line, it is stationary. We have got, if the body is at constant speed, okay, so for example, the middle of the 100-meter sprint, distance and time will work in this linear fashion as so. Now, if a body is accelerating, we would get an upward curve with regards to time and distance travelled. The distance travelled is shorter when time is longer due to us accelerating. Okay, so for example, at the start of a 100-meter race. The body is decelerating, and they'll be decelerating at the end of a 100-meter race as they've crossed the line. And the curve will be a downward curve. It would start like so. As distance increases, time, all of a sudden, as time goes on, distance will not be increasing because we're slowing down. So that's distance time graphs for you. We then need to be aware of speed time graphs. A speed time graph shows the speed of a body over a particular time, and the gradient of the curve indicates the acceleration or deceleration of the body at a particular instant, or if it's just at constant speed. So if a body is accelerating, we'll have a horizontal axis will be time, vertical axis will be speed, meters per second, and the line will have an upward curve. If the body is at a constant speed, we will have the speed not changing, obviously, because it's constant speed. It's uniform speed here over time. If a body is decelerating, it would be a downward curve as we will slow down as time goes on. We have velocity time graphs. So velocity time graphs, and these are a representation of the velocity of a body over a period of time. And again, looking at acceleration, deceleration, or constant velocity. So if a body is at constant velocity will not be going up or down over the period of time. If the body is accelerating, there'll be an upward curve as time goes on. And then if the body is decelerating, there'll be a downward curve as time goes on. Okay, we also need to be aware that we can show a velocity time graph in particular parts of a race. So for example, a 100-meter sprint, there'll be a part where we're accelerating, a part where we're at constant velocity, and a part where we're decelerating. The same with a swimming race. Also, we need to be aware that with a velocity time graph, we can show a change in direction as well. So here we have acceleration, deceleration, nothing happening, change in direction, accelerating, changing direction, decelerating. For example, passing a ball. So it'd be a forward pass, the ball accelerates, it decelerates, the other person stops the ball, the other person changes direction by kicking it back, it accelerates, decelerates. Okay, so any time the curve crosses the x-axis, the object is changing direction. Okay, so please make sure you have good key notes on that, and I'll see you in lesson. Thank you.